Dr. Karthik Vaidhyanathan, who is an assistant professor at the International Institute of Information Technology in Hyderabad. He is also the project partner through which we have this 3 days summer school that has been organized. So via the Digital Twins for Intelligent Transportation Systems project, which has been funded via the UKIERI. So just a bit of a brief from about Karthik. He's he's also associated with the leadership team of something which is called as the Smart City Living Lab at IIIT Hyderabad. I visited there. It's a fantastic place to see. Main interests lie in the intersection of software architecture and machine learning with a specific focus on building sustainable and self-adaptive software systems. So yeah, quite an interesting and a niche area to work in. He also is quite active in organizing conferences. One of the most recent one was IIIT 2024 at Hyderabad, and he's also on editorial board of IIIT Software, and also has industrial experience in building and deploying ML products and services. So a bit of a mixture of academia and industry, which is what we would be looking to see in his talk. So welcome, Karthik.
Thank you. Great. Okay. So very good afternoon all. It's a session post lunch. It's just very challenging for me too because I also had lunch. So I'll try to keep you as much as active as possible. So first of all, thanks Dr. Puro and Ramona for organizing this event and for inviting me, because of which I could be here. Before I start the talk, I would like to bring into your attention some important things, right? So Apple recently launched iPhone 16 2 days back. I don't know how many of you followed it. Prior to that, like 3 months back, Apple launched something in their WWDC. They said something called Apple Intelligence. So the idea was about how can I put AI on your phone, right? Where the AI can help you with multiple things. And of course, Siri now being powered by a very powerful AI, let's say ChatGPT and so on, right? And then of course, few months later, if Apple launches something, then of course, Microsoft and Google has to pitch in, right? So Microsoft came up with this idea of Surface Pro, which was powered by Qualcomm Snapdragon. And they said that this is going to be a Copilot PC, where you will have a Copilot with you, which is powered by the very powerful language models, and you can talk to it. It will help you with multiple things and so on. Of course, Google said they are not behind either. They also came up with Pixel 9, and it also supports AI. Now, why I'm saying this is on-device AI is becoming a thing, right? Devices which can support AI. Device where you can run powerful AI models. If you can enable that, then probably you're solving a bigger problem. But the question that that comes up is, if we are talking about on-device AI, how mature it is, how much challenging it is to build something like an on-device AI, and what are the better mechanisms that we need to engineer into these systems so that these systems perform as they are expected to be, right? So that's what we are going to talk about today. So what we are going to talk about is about self-adaptation meets edge AI. So the idea of how can we create something that can autonomously adapt so that the performance is guaranteed and so on. And we are going to see a specific aspect of something called model balancer, which is based on the recent work that we have been doing over the last 3-4 years and so on, right? So thanks, Puro, for the wonderful introduction. So before I start, I would just like to give a glimpse of what I've been doing. Brief about me, of course, I work in the Software Engineering Research Center at IIIT Hyderabad. So IIIT Hyderabad is one of the premier institutes for computer science in India. And we don't have this notion of departments and so on. So our entire institute consists of like 27 research centers focusing on multiple aspects of computing research, ranging from software engineering, AI, robotics, and so on and so forth. And part of what I do is I'm also a leadership member of Smart City Research Center, where we have converted the entire campus into Smart City Living Lab. We also have a person who has worked here, Rio. Prior to this, I did my PhD and postdoc in Italy. So my PhD and postdoc was in the intersection of software architecture and machine learning. So I consider myself as a little outlier here. I can give a very important perspective from a software angle, but not too much from a networks or hardware angle. But I believe that integration is very important, right? So I have a double master degree, one specialized in machine learning, one specialized in software architecture. So somehow I ended up doing PhD in the intersection of both. So that's my research interest, more from machine learning to software architecture. So how we use machine learning for continuously improving software systems, and especially looking at something like recently for the last 2 years, we have been working on how do you use generative AI for architecture knowledge. We will touch upon some of those in today's talk. On the other side, I'm looking at how can you build or how can you engineer machine learning systems or AI systems, right? There are a lot of challenges in building such systems. So how do you go about that? And we also look into something called autonomous MLOps, which is becoming a very important thing these days, right? So yeah, some fun facts. Of course, in UK, I can happily say that I'm a really cricket lover because many times I go and say this, people will be like, "What is that?" Right? So it's a very popular sport here, so I can happily say that. So I'm from Kerala. We also call it God's own country, from the south of India. So that's a brief about myself. But let's move on, right? If you look at the world of computing, we have come a long way, right? We have started probably with a room that used to be like a computer to something that can, probably be there in your finger as a smart ring that can do a lot of processing today, right? To the extent that what this computer on that side used to do, today your smart rings can do much better than that, right? So that's where we have grown over the years, right? I mean, today we are talking about smartwatches, your Apple watches or whatever watch that can actually pick up things, perform some kind of computation and send it to some cloud and so on. So the question, and of course we are even going beyond, right? Today we are talking about why do I even need a device? Why do I even need computing? Can I think about spatial computing where everything else, everything is a screen for me, right? Apple released Vision Pro, right? So what we are increasingly coming up with is we are trying to reduce the device size, at the same time increase the computing capability. So that's where we are going, right? And we are also talking about when I'm doing such a reduction, can I bring some AI capabilities? Can I bring some intelligence capabilities? Because that's when we want to say, oh, this is wow, man, this is amazing, right? So that's where we are going. But on the other side, right, with the hardware getting improvements, AI has also matured. So, and of course, it's because of hardware that AI has matured. That's how I would like to see. Because 1943, we had the first AI that came up, right? McCulloch's, they came up with this idea of MCP neural net, right? So MCP was the first neural net. The idea was, how do I emulate human brain? And of course, they said, what? Human brain consists of a set of neurons, and they all process information together and come up with some output. So they said, can we build the simplest form of it? So they said, okay, I'll take one neuron, I'll give some input, the neuron will process something and generate an output. So this was the starting point of what we see today as the revolution of AI, right? And then, of course, in 1950, we had the Turing test, the famous Turing test from Alan Turing that came up. And of course, in 1952, the first checkers game, a bunch of rules, and the computer is automatically able to learn how to play checkers. And 1958, from then, what happened is a lot of revolutions happened, right? The first important milestone that happened is the invention of something called perceptron. So perceptron actually came up with this idea that it's not about one neuron, you can have multiple layers of neural network that can process the information and then generate an output. So that became a big thing. Along with perceptron, what also happened is something called backpropagation came. So I can have a layers of neuron that can process information, generate an output. I see how much the output is different from the expected output. I see what is the error, and I propagate it back to the network. So just like humans learn, can I, build it into the neural network? So what I'm trying to say is, it's not that because the ideas were not there, the ideas are already there, right? It's just that the computing power was not enough in order to process so much of information and so on, right? And what happened, of course, in neural network, if it involves a lot of matrix multiplication, a lot of differentiation, right? A lot of linear algebra goes into the picture. So the question was, computing was not capable enough to handle such load, right? And of course, over 1997 to 2000s, and if you see now, we are talking about GPTs, different versions of GPT, so on and so forth. So the question is, okay, AI has matured over the years, then why don't we, put it somewhere in a smaller device? So one of the biggest revolution that has also happened with AI is models have started becoming bigger and bigger and bigger as the years progress, right? Along with, of course, the improvements in hardware. So if you see today, we are talking about the stat GPTs and so on, they are having some billions or even billions and trillions of parameters. Now, what I mean by parameter is if you just take a slope of a line, the equation is y equal to mx plus c. So if I give you an x value, in order to get a y, all you need is an m and a c. There are two parameters there. right? But in a complex set of neural network that has multiple layers, each neuron will add a parameter, and the connection between one neuron to another neuron will, add multiple parameters. So our brain has trillions of such parameters that is processing one single information. Our idea is to emulate human brain, right? So the networks has also grown. So today we are talking about networks with trillions of parameters. Now the question is, okay, Karthik, you are saying all this, what are we coming into? Right? What I'm coming into is, today, if you want to build a model, it has become so easier because AI is very accessible. The whole idea of all this has been how do you democratize AI, right? So today, if I have to build a large language model, I can easily build it. But of course, I need a lot of money because I need to buy compute power, right? So how do I build a large language model today? Of course, I can take all the text in the internet, maybe 10 billion, 10 billions of text from the internet. I can put it in hundreds of GPUs, and I can train a transformer neural network. Of course, that is what has been powering the GPT, right? And then I can generate a model. This model itself will be some billions of parameters with hundreds of GPU size, right? I get a model, and this model, if I give some input, it will generate something. Whether that output is good enough or not is a different question, right? But I will get a model. So this is not made up, by the way. This is Meta 2 of Llama. I mean Llama 2 of Meta, right? I mean this is actually a model that has been developed, right? It followed this process. But the question is, can I now put this on a small device? No, right? Because I'm talking about hundreds of GBs of data. How do I even put it on a small device? And the other thing is, we know what is the capability of GPT today. What is the capability of different types of language models that are there, right? Every organization wants to use it. I go to some company, they're like, okay, can you create a Copilot for us? Can you create an LLM model for us? But the biggest challenge they are all facing is this issue called the blurb issue, right? There are a lot of issues that come up because the first thing that they say is, hey, you know what? I want my AI to run on a small computer, right? Of course, yes, but the problem is I cannot easily do it. But if not, what is the solution? Put it on the cloud. Now in cloud, what are the challenges? I am running in a laptop, some model. Now I have to send this data from this laptop to the cloud and I have to get the data back. So there is going to be a significant amount of latency, and I need to have sufficient bandwidth where I can send that much data and get the response. So these are the challenges. Of course, the more important challenge is, as an organization, I don't want to give my data to some third-party provider. I don't want to give my data to GPT, right? We know EU rules are very strict, right? I'm sure that we have come up with a lot of laws that have recently come up in terms of using AI. The problem is, how do you safeguard your organization-specific data, right? So this has resulted in a lot of issues. Of course, the cost. I don't know if you know, GPT every day in order to sustain your chat GPT, right? OpenAI is spending like crazy. They have not got the ROI back. Every day they are spending some millions of dollars of money just to ensure the system is up and running, right? So, but the question then comes is, how do you take it to edge? Can you take it to edge? Because that's the whole point, right? Now I know that cloud is great. It provides amazing capability. I can run all these huge models, but there are a lot of challenges that I face as an organization, right? I don't want to give away my data. So privacy is the most important thing, right? So this means, can you do edge AI? Now, what is edge AI? In a very simple, definition, all you can say is it's just a process or it's just a mechanism where you do AI on the source or closer to the source where the data is generated, right? That's it. So any device, if it has capabilities, whether it is generating some kind of data, if it can run AI there, of course you can say that you are in somehow accomplishing edge AI, because these nodes or these devices are at the edge of the network, right? Your mobile phones, your laptops, they are all, devices that is gathering some amount of information. Now, can I have an AI that is running just there, process the information so that I don't have to send so much data to the cloud? Maybe I just send some processed information to the cloud. That makes it much easier. And if you see, EdgeAI market today is valued at a huge amount of money. Today it has even grown up to what, 15 or 16,000 million USD. And by 2030, they are projecting it to go by even 21% higher than this. So it's a huge market out there, but there are a lot of challenges that comes up when you want to say, hey, I want to do EdgeAI, right? And what are those challenges? Of course, these are no-brainers, right? Edge is always constrained by resources, right? Of course, there is a limitation on how much compute power you can get. The moment you say, I want to run an AI model, it means that you're calling for, faster computation, faster amount of processing, and so on, higher amount of processing capability, and so on. Security is a big problem. Of course, it is kind of thing that it's like a double-edged sword, right? It works because of the fact that I'm not giving everything to the cloud, but at the same time, attacking an edge device might be much easier compared to attacking a cloud because you have to have strong security policies at every edge device in the network, right? Then the biggest question is, if I am putting a heavy model, in order to put it in the edge, I have to do something called compression and quantization of the model, where I compress the entire model and I put it on a small device. Now, this compression process might result in a challenge where the accuracy of the model might drop. So how do you compress your model without dropping much accuracy is a big question. It's a big research that is going on there, right? So that's definitely a challenge. And of course, communication, because you're running on the edge. The biggest question is, can you guarantee that there is a reliability on the edge? Because you are processing the information, you might have to send some data to the cloud and so on. What if the edge suddenly dies off? What if suddenly the communication link doesn't exist? So how do you handle this, right? So this is where we have been like, okay, all these challenges exist, and EdgeAI is bringing a lot of advantages, but it also comes up with its own challenges. But the interesting thing is, AI systems in general comes up with a lot of challenges, right? It's not just about EdgeAI, but I want to talk a little bit from a systems angle. AI, just building an AI system is not as easy as you think. Of course, we have democratized it, or we are trying to democratize, but it also has its own challenge. So Google in 2015 came up with a very interesting paper, right? The paper is titled Technical Debt in Machine Learning Systems. So it was published in UX, one of the top conferences in machine learning, right? And what they said, in an actual system, ML code occupies only probably less than 3% of the entire system. The rest of the system is all about how do you make that ML code work, right? How do you ensure that you have mechanisms to get the data? How do you ensure that you have mechanisms to get predictions from the ML code, right? So all this have to be built in to ensure that that small piece works. And even worse is this stat. Gartner says that more than 50% of ML systems don't even make it into production, right? They're all prototypes that exist in the organizations or wherever, right? You build a lot of things, but nothing goes really because there are a lot of challenges, systems suddenly fails, and there are a lot of uncertainties that comes into the picture. So what are those uncertainties? So if you look at a typical ML pipeline, it looks something like this, right? You have some kind of request that comes into the system, you do some kind of data pre-processing, then you do some kind of inference. Now, by the way, this is an inference pipeline. This is different from training pipeline because training is a batch process where you train a machine learning model. It takes days, hours, weeks, depending on the kind of model that you're training. Inference is more like a real-time process. You send some information, you use a machine learning model, and you generate a prediction, right? So let's say this is the inference pipeline. There are so much of sources of uncertainty that can come in. One of the uncertainty is resources. Do you have enough resources to process the information that is coming in? A. Second thing is data distribution will suddenly change and the data will drift. So how do you handle such data drift? Model predictions will start drifting from over time, right? All this will have another impact on the overall performance of the system. At the same time, also depending on the size of the model you use, the type of the model you use, the latency of predictions will differ, right? It might give a higher accuracy, but at the cost of response time, at the cost of throughput. So now the question is, how do you balance all this, right? So considering uncertainty, what has happened is in the software, systems literature, at least ever since 2003, when this paper came up, the famous paper from IBM, right? It's called the Make-K paper, or the paper is titled as The Vision of Autonomic Computing. So Keffart and Chess, they came up with this very interesting idea. They said, what if software systems could adapt like human cells, right? Can auto-configure themselves, can heal themselves, can adapt themselves, right? Can we do something like that? If we can do this, it means software systems probably may not require much human intervention. It can autonomously understand how to, improve and handle itself. It's a very interesting concept, but of course it takes a lot of challenges to build such a system, right? So they came up with this idea. They said, for any software component or any system, you can treat it as a managed element to which you can attach an autonomic manager, which constantly monitors what is happening in the system, analyzes if there are some issues, plan what needs to be done, and executes the adaptation on the running system, right? And if you continuously keep doing this, you ensure that the software system works as it is supposed to be, right? So this resulted in something called a conceptual model of a self-adaptive system, right? So the conceptual model says any self-adaptive software system consists of two parts. One is the running software system, which is your ML system or any software system, and then to which you can attach something called a managing system, which can constantly monitor what is happening in the system and adapt the system. This managing system will have a set of high-level objectives. The objectives can be ensure that my system never fails, ensure that my system is always guaranteeing a response time of 0.6 seconds, ensure that my throughput is something like this. So all these objectives can be encoded, and based on this objective, this managing system will have some kind of mechanism to guarantee that the software system is going to accomplish the objectives. Okay? So this was what proposed in the conceptual model of a self-adaptive system. So ever since then, a lot of work has been done. And most of the work, as you can easily guess, was about how do you make that self-adaptive software system intelligent. So can you use machine learning techniques to do that? Yes. So over the last 20 years, many different machine learning techniques have been proposed in order to build self-adaptive software system. Machine learning techniques, control theoretic techniques, formal software mechanisms, many things have been developed. But the question then comes up is, yes, you can use machine learning for self-adaptive, but can you self-adapt a machine learning software system? So this is something that has been unanswered, right? And even if you can do, what kind of adaptation can be performed? So here is where we came up with a very interesting idea. I believe it's interesting, yeah. So just to give a very intuitive idea, right? If you look at LLM world today, you go to ChatGPT, right? If you are a GPT-4 subscriber, you can go there and you can see there are multiple models that you can choose. If you go to help.openai.com, they will give you different models and when they can be used, what is the cost, and how fast they are, how accurate they are. So much of profiles will be there for each model, right? And you have this collection of different models that we have available, we are having in our disposal today. They are open source, they are proprietary, and so on. Similarly, in vision also, we have a lot of models for the same task, right? For example, if you want to do object detection, which is nothing but detecting that there is an object like a person, a car, and so on, and a given image, you have a bunch of different types of machine learning models that are available. So for example, this is something called YOLO, right? YOLO is one of the classical models that are available in object detection. You see, all these are different models, variations of the same YOLO model, but you can see depending on the size of the model, you can see different variation in their accuracy, you can see variation in their speed, number of parameters, and so on, right? So the big question that we started asking ourselves is, can we switch between machine learning models in runtime based on the context? Can I decide based on the context, okay, you know what, now I need to use this model versus the other model, right? And this can allow me to balance in such a way that I can somehow guarantee the quality of service, right? So this is exactly what we proposed in our first work in this direction. So this was published in ASE, which is Automated Software Engineering at the A-Star Conference in Software Engineering. So what we said is, can we create a mechanism which will allow us to switch between machine learning models in runtime in such a way that I always guarantee whatever quality of service trade-offs that I have, right? So the first work what we did is we wanted to ensure that the system always guarantees particular response time without compromising on the accuracy. When you have too many requests that is coming into your system, how do you balance between machine learning models, right? So, but this work, of course, the question is, how do you implement it? We came up with an unsupervised learning mechanism that understands how to decide which model to be used for a given situation, and based on that, we were switching. And we, of course, implemented this on a very small software system that we built. So we built a object detection service, and this, of course, was running in your laptop, right? Having these different models, except large, because large is something you cannot run on a laptop. It's a huge model. And we use a FIFA 98 benchmark race to constantly hit the model using COCO 2017 object detection dataset. So we were constantly sending the images to the model, and we were switching which model to be used based on the image that we were sending. And the characteristics of the image were parallelly learned by using an unsupervised learning mechanism. I'm not going into details. This is just giving an idea, right? So we performed some kind of course, an analysis. We saw that there was of course, in this case, we saw 39% improvement in quality of service, and the time taken to switch between model was less than 0.01 seconds. And of course, our approach was guaranteeing a very high utility. So utility is something that kind of combines the response time gain as well as the loss in terms of accuracy, right? So how do you reduce the loss in accuracy, but at the same time improve your response time? So that's what the utility score does, right? So this was great, but the question we had is, what is the point of building something like in a research paper? Of course, you get a nice paper, but you want to do more than that. So what we created is, we created an exemplar system. So an exemplar is somewhere you can actually download it, you can test it, you can work with it, you can play with it, you can add your own logic for model switching, right? So we wanted to release something to the community. So we came up with something called Switch. So this was published in SEAMS 2024. It's again one of the premier conference for self-adaptive software system. So what we built is, we built the entire logic of model switching as well as a system where you can actually perform this kind of switching, right? So this system is actually available to download. right? And this is, I mean, anyone can actually perform and experiment different strategies. So here you can see a glimpse of Switch. So you have a nice dashboard which shows what models are running. So you can see different models here, different YOLO models. You can even see how much percentage of different YOLO models are used in runtime. So you can select a data set, you can select the set of models you want to use, and you can give it to this mechanism in this system. It will automatically switch between the models, and you can see the statistics of switching, and you can even download the experimental results. This allows you to even compare with our own baselines, and you can come up with a better approach for model switching, right? So of course there is a demo that I'm planning to show if we have time, but this is a PDF, so I cannot show it. Pardon me for that. Maybe towards the end we'll show a small demo. Yeah. Okay, so we didn't want to stop there because we said, okay, this is something with very respect to response time, and we were able to do something. But if you see, one of the biggest killer of sustainability, we talk about many things in the software themselves, right? So it is estimated that software's energy consumption is equivalent to air, rail, and ship combined. That's the huge amount of energy we are talking about. So, for example, they say in a very lighter note, if you want to save energy, if you want to save planet, stop streaming in Netflix, because Netflix consumes energy that can power 45,000 households in the US, right? So we don't want to do that. So now can you come up with better software mechanisms to handle it? Okay? So we came up with this idea where we applied the switching concept. Now with energy consumption as as a big objective for us. So now can you switch between different machine learning models by reducing the energy consumption? But for this, we did use an unsupervised learning mechanism because, of course, to save energy, you don't want to use an unsupervised learning which can consume more energy, right? So we came with a very lightweight epsilon greedy strategy, which uses a probabilistic approach to switch between machine learning models. And of course, we were able to get very amazing results, right? So we were able to see that our approach, which is echo MLS, with different values of epsilon, was able to perform much better than the other state-of-the-art approach that you can think of, right? So this is great, but the question was, of course, this all works in your laptop, but can you take it much into a lower device, much to a smaller device, right? So this is what we did with Qualcomm's QIDK kit. So Qualcomm, with IIIT Hyderabad, established something called Qualcomm EdgeAI Labs, where we could actually play with their latest prototype device, which is called the QIDK. It's Qualcomm Innovators Development Kit. The idea of QIDK is, as a developer, you can come up with different mechanisms. You can actually implement it here, which is nothing but a state. It's running a state-of-the-art Qualcomm Snapdragon chip, right, which is powering Samsung Galaxy S23. So you can test everything here before you actually take it to the deployment. So what we did is we said, why don't we put our model switching concept into this? Or can we even do that, right? So it provides support by which you can bundle your entire machine learning model into an Android application and you can run it. But nowadays, they are also supporting Linux, right? So we did that. So we exactly did that. We took the model balancer concept, we deployed it in QIDK, and we can see that these are the different models we used. Of course, we didn't use YOLO because YOLO is very heavy. We used smaller models that can run on mobile devices. And we could see that our kit was able to even perform much better than the results reported by Samsung Galaxy and Google Pixel, right? Pixel 4, by the way, okay, not Pixel 8 or anything. Yeah. So this is an app that we built, so we can actually switch between the machine learning models. So again, I have a small demo here, but maybe in the end we can see that. So here, actually, while running the app, based on the traffic conditions, it will switch between the machine learning models. To guarantee that your battery consumption is not so high, because one of the biggest challenges in mobile devices is to ensure that your battery drain is as less as possible, right? So based on this work, we were invited for Qualcomm Developer Conference 2024. We also presented this work in Qualcomm's University Platform Symposium. We were selected one among the 40 universities in the world to exhibit what we have built, right? And of course, we are doing many more works in this direction. But we didn't want to stop there, right? So that is only computer vision. The question that you can ask is, hey, you started with LLM, where are you going now, right? So we tried that also. So we said, there are a lot of large language models available. There are a lot of language models that can actually run on your laptops and even smartwatches today, right? 5.2, 5.3, and so on. So we said, can we take all the large language models that are available and train it on a very specific domain? So the domain, I'm not going to explain much of the domain. The domain is something called design decision making. So in software systems, if you want to come up with a decision, right? For example, you want to decide whether you want to use MySQL database or an Oracle database, right? there are ways by which you can document this and you can generate decisions. So here we build a copilot where you can go and ask a question and you generate a decision, right? So what we did is we fine-tuned different models on the decisions. We also did zero shot, few shot, and so on. And we saw that when you fine-tune a very small model like GPT-2, right, which can run on your small machine, it was almost performing on par with something like a GPT 3.5 and close to GPT 4, right? On a very specific task. Now, what I mean to say is, if you build a domain-specific LLM, which is very small, it can, if you fine-tune it with enough data, it can perform on par with probably larger models. Because larger model has all the information in the world. But you only need something that is very specific to your context. So I believe that for EdgeAI to happen, in terms of LLM, this could be a very interesting direction, right? But of course, this is very specific to Edge, but I believe that EdgeAI cannot just stop there in Edge, right? You have to go much beyond that. So the question what we were thinking of is, can we now start leveraging something like Edge Cloud Continuum, right? Edge can do a lot of things. It has its own advantages as highlighted in green, but cloud also provides a lot of advantages, right? You can train heavy models, accuracy is amazing, the scalability is not affected. On the other side, Edge has challenges with terms of accuracy, you cannot deploy larger models and so on. So instead of just switching between models in Edge, can you also leverage between Edge as well as across Edge and cloud, right? So this is something that we are working with. So we are saying, can we build intelligence into the system where it can decide when to use cloud versus when to use Edge, right? So essentially it boils down to something like this. You have Edge, you have fog, you have cloud. So can we dynamically adapt between them? So it's not a new thing. We have done something similar in IIIT 2020, which is like 4 years back. We had a very nice paper where we said, in an IoT system, can we switch the processing between Edge versus fog versus cloud in such a way that you can optimize energy consumption and performance, right? We use a reinforcement learning based approach combined with something called formal verification to do something like this. It was a candidate best paper in IIIT 2020. But the question, this was not for ML system. This was using machine learning for a non-ML system. But now we are talking about machine learning systems. So we are thinking if we can adapt some principles from this. So these were the implementation for that particular work. So this is what the approach we call RLMC. And we could see that this approach was able to give higher utility compared to the other approach of just using Edge or just using fog or just using cloud, right? So the hybrid always works. That's what essentially I want to say, right? So going forward, I believe there's a lot of opportunities in this field, right? One of the biggest opportunities is using this idea of Edge Cloud Continuum for self-adaptation. We cannot always rely on cloud for everything. That is what, of course, everyone have already taken steps. Microsoft, Apple, Google, all the organizations are taking that step. But the question is, can we also do it proactively, right? Can you prefetch some resources and keep it ready in the Edge without waiting for the cloud? We also want to talk about EdgeAI Ops, because so far no one has talked about it. People are talking about EdgeAI, but you have to constantly improve the machine learning model, version the machine learning model. So how are you going to do that? How are you going to build pipelines around these kind of systems? So this is a big question that the community needs to answer. And of course, how do you optimize EdgeML on scale? Can we have, say, for example, a traffic light scenario, right? You can have multiple traffic lights with CCTV cameras and having each running different machine learning models. Can I use this in such a way that we can switch the machine learning model in the edge based on the traffic scenarios, right? And can they communicate between each other? So there are a lot of interesting questions. What about domain-specific LLMs on the edge, right? So we are working on something called SLMs, small language models, that can run on your laptops, on your watches, and so on. So can we optimize SLMs and create a collection of SLMs which are where different SLMs are capable for different particular tasks, and you can switch between the SLM based on the query that comes from the user. So can you do something like that, right? So these are some things that I want to talk about. So if you have not been listening to anything because of the afternoon lunch, and suddenly you woke up, okay, this guy is ending the talk, let me see what he's trying to say. These are the key takeaways that I would like to leave you with, right? So the first thing that I want to say is, of course, there is an increasing focus on edge systems. We are talking about how do you improve edge and so on. And of course, AI models are getting bigger and better and better accurate. People are talking about if GPT-5 comes, everyone will lose the job. Personally, I don't think anyone is going to lose the job. It's just that we have to upgrade ourselves and AI is going to help us, right? That's what I feel, of course. But the bottom line is handling uncertainty is the key, right? How do you handle uncertainties? Because in real world, your software system is going to be subjected to uncertainties. So can you come up with better engineering mechanisms so that you can handle this, right? So that's why I feel that there is a need for better ways to architect or engineer AI systems, especially EdgeAI systems. And from a hardware perspective, I feel we also need better hardware accelerators, efficient neural processing units that needs to come in. The Google released G4, chip in the latest Pixel, but I feel better hardware accelerators are the need of the hour. We also did a Dux tool on software architecture and machine learning to see where the community should focus on. So you can see the report here, you can scan the QR code and you can read the report. We are not talking specifically about EdgeAI, but we are talking about what are the challenges in ML systems, and of course, all that plus the challenges of the edge applies to edge systems, right? So we believe that there is a lot of research that needs to be done in the coming days. So I just want to thank my team because, of course, this is a huge effort by multiple people. What you see on the right is my team. We call ourselves SA4S, Software Architecture for Sustainability Society. So I have my two PhD students and master's students, honors students, and so on, right? And of course, I'm here because of the project Digital Twins for Intelligent Transport System, as Purav mentioned. So the team, along with me, this project is headed by Deepak, and then we have students Sahil and Kia working on this project, right? So thanks to them because of all their efforts, I'm here to speak. Of course, all the achievements are theirs and the mistakes is mine. So I hope you enjoyed this talk. And of course, feel free to check our website to see what kind of works we have been doing. Of course, this is not the only work we are doing. There are a lot of streams of work on generative AI, software sustainability, digital twins, verification of ML systems, certification of ML systems. There are a lot of interesting work that we are doing. So hope you like it. And of course, feel free to scan this. And IIIT software is something that I'm associated with. There's a podcast called NC Radio. So please, amazing things are being put up. So hope you get some time to listen to that as well. So thank you. Thank you so much for having me. You have time to show a small demo? Or?
Yeah.
Okay.
Maybe one of them, yeah.
So the one that I was talking about is this. Okay. Okay. Yeah. So this is what I was talking about. So this is a system that runs, and of course, don't mind the code that is going here, right? So essentially, what happens is, so once you start, you can upload a file. So you can upload whatever zip file with a collection of data that you have, and an image file, and then you can choose a CSV file, which basically says how frequently you should hit the system. So this you can either use from a real world, or you can create your own different kind of simulations that you want, right? And once you do this, what happens is of course, we are just showing what is happening behind the scenes so that you feel that it is not a demo that you're faking, right? And it's actually working. So there's a dashboard that gets generated. So once the system starts running, you can actually see different machine learning models in use. So here you can see as we start hitting, we are getting the request. So it is actually hitting our machine learning model. And this model is going to switch now based on the condition, how many requests are coming into the system, what is the average CPU, what is the average confidence. Based on that, I'm going to keep switching between the machine learning models. Of course, this is run using ELK stack, Elasticsearch, Logstash, Kibana. So people who know the stack, this might not be a surprise, right? And of course, you can see that the switch. So in real time, you can actually see this working. You can see how many emails we have processed, what is the utility currently, and what model is being running, and so on. So all these details are displayed, right? And what is the time taken? What is the confidence score? So 0.66 means we are giving any detection with a 60% confidence. Okay, so that was about this particular system, and yeah, okay. So you have all the stats that is coming up. On the other side, there is also this very small, it's actually like a GIF. Let's see. Oops. Yeah. Okay, so this is the one that I was talking about, right? So you can actually see model is being switched. when the system is running. So you can see that there are different models, and based on that, you can see the battery consumption and values keeps changing based on what model you use, right? So this is a small demo where we are using QID kit, and the other was the one we were using at MLS, which is the switch exemplar that is available outside. Okay, so thank you again for yeah.